Okay, good morning, everybody. This is the second lecture from week 2 in seismic engineering. And today we are going to talk about strength and stability considerations for seismic applications. The lecture as it stands evaluates what's the implication of other criteria than strength that most of you familiar with from prior design classes, and the impact of these criteria into the overall design process, and most importantly for seismic applications. The objective of today's lecture will be to introduce some basic strength requirements that you are all aware of. I'm not going to stay into this too much. Then I'm going to go into what we call second order effects and how do we tackle those to ensure stability for frame structure in particular, because these effects are important for these types of structures. I will also talk about allowable ductility and how this is linked with this, and then eventually I will talk to you about an example so that you can see how this comes together. In typical design classes, for instance, this is an example from frame structure. Usually what you are, most of you familiar with is that you essentially get the forces that you anticipate on a structure. So in this case, I have lateral loading going on in the structure at this level and at this level. Assuming you can do the statics, and suppose you are looking here at a member, you are going to deduce the forces in terms of moments, shear, as well as axial load. And then if you know the forces on the member, what you're going to do is that you're going to go through a number of design checks to ensure that the member has sufficient strength to carry these forces. For instance, since in this case we talk about columns, if we look back into columns, usually you're going to design a column of this frame to resist the axial load that you anticipate. So that would be this one. And then from my typical design class you did, you have to check the column for compression and buckling. Because you have axial load and bending from what we saw before, you will have to check the column depending on the orientation of the strong axis and the also orientation of the primary bending that you see, the interaction of axial load and bending. And in a case where the column is oriented with its weak axis, the axial load and bending again has to be considered, but in that case, the weak axis bending. And of course, in the general case, if you have axial load bending interaction and you have bending in both axes, then in this case, the interaction is the complete interaction that you have to consider. So these are typical strength verifications that you have to consider. This is one of the many examples we could consider. If we go back here and we look at the beam, of course, there is, if we think about the moment diagram in the beam, it's going to look like this. And of course, here where I have the location of the maximum moment, I will have to, another strength verification I have to do is I have to ensure that the flexural resistance of the member I'm picking here is basically larger or equal than the flexural demand that I will have here at the end. And similarly, when I'm looking down here at the foundations and so on, I basically have to do the same. So these are typical strength verifications. However, uh, in addition to strength verifications, and in particular for seismic loading, you should also be very cautious with deflections. And deflections could be very crucial because they relate to stiffness of the element. And strength and stiffness are completely different properties of a member that are indeed related to each other. Because if, for instance, you try to increase the stiffness of a member by changing the geometry and trying to increase, for instance, the moment of inertia, that will also have an effect on strength. But as properties, these are two different properties, one affecting deflection, the other essentially relates to strength. So in the example here that I'm showing you, just to emphasize on the importance of deflections, you see a fishing rod in this case, which is extremely flexible because it's been designed to be so flexible to accommodate these deflections once the fish bites the food that you put to catch it. And in order to be able to be so flexible, it's also very strong. However, if you are looking into structures, and in particular floor systems and general structures, they cannot do this for several reasons. So, for instance, a frame structure or a floor system has to be strong, but has to also be stiff enough because it cannot have the luxury to deflect like a fishing rod. So the reason for this is that when you have large deflections on frame structure, these will cause additional demands, where we call them second-order effects, that will amplify the design forces that you're supposed to use to design the members of the structure and ultimately the structure. So what do I mean by that? So suppose that you have here the frame that is highlighted with black color, and I assume for the sake of the example that this is a pinned frame. And in addition to the lateral load F, you have gravity load N1 going into one column and 2 going into the other column. Now, by conventional statics, if you would like to compute down here what would be your shear force on the supports, then from conventional statics, if the stiffness of this column and this column are the same, then you're going to say that, here you're going to have VE over 2. Here on the other support, you're going to have VE over 2. And the summation of the two is going to be equal with the lateral force F. So that would be pretty much this condition here. However, this assumption implies, or this solution implies, that your deflection here, delta 1, is relatively small. Otherwise, since your frame is deflecting by a large amount, because the gravity load that you have on the individual columns is also displacing by the same amount delta 1, this essentially creates an additional shear contribution that is known to be equal to shear because of P delta effects. So in that case, if I want to consider here the exact expression for the total shear that I should consider in my design, in this case, it would be, of course, VE, which is equal to F, but it will also be an additional term here that is going to be equal to, in this case, N1 plus N2, because this is the total gravity load that is being translated by delta 1 multiplied by delta 1. So that would be the second order moment. And then if you divide by the height of your story, that would give you pretty much a shear force. So you can imagine that we cannot allow large deflections to a frame because these deflections essentially amplify this particular term here. And the more you amplify this term, the more you increase the shear here. And if this is not taken into consideration in the design, then of course your design is not going to be conservative, but it's going to be non-conservative. So let me clear a little bit the slide here. Okay, so here essentially you see what I just showed you, that the V total is basically equal to that. Now, the implication of this, if you are looking at, for instance, the same type of system I showed you earlier, but now I'm using a little cantilever, is that if you look at the relationship between the shear that you have in the structure versus the corresponding deflection, if we assume that the system is linear, so there's no nonlinearity in the system, this particular term here, what it does to the capacity of your system is that at a particular displacement delta 1, you are going to have a drop here in strength that is going to be equal to this particular term here that represents the second order shear because of the amount of deflection you are allowing the structure to go. So that means that if you're looking at the capacity side of your structure, instead of your structure to be able to resist this much shear, because of the second order effect, essentially you are losing shear, and the actual capacity of your structure is basically this one down here, simply because of the reduction in the presence of P delta effects. So there are good reasons why we would like to keep deflections within a reasonable range when it comes to frame structures, because we would like to limit the influence of this second order effect that essentially relates to the reduction of the capacity on one side and the increase on the demand on the other side, as we saw in the previous slide. Now, as I explained, P delta effects on frame structures will have an impact on the forces you are measuring. So in particular, if I'm dealing here with a frame that I show that has a height of L, and I apply axial load N on both columns and horizontal load H, then by conventional statics, if I try to sketch the moment diagram because of the forces that I have here, I will neglect N, because usually you assume in this case that the deflection of the frame is actually not large for the given set of forces you have. And in this case, your moment diagram is going to be pretty much the moment diagram I'm sketching here. Now, this is the moment that I will get from first order analysis that essentially is the same with the type of statics you did during your first year, or the statics 2 you did during your second year, to deduce pretty much the member forces on frame structures. However, if we now consider the fact that a frame could displace by appreciable amount delta, then this moment diagram is not going to be the correct one to be used in design, because essentially these forces are going to amplify the moment diagram on your members. In particular, if I wanted to sketch the real moment diagram, it would more or less look like this, because the displacement delta essentially increases the moment diagram on the members uh, because of the second order moment or second order shear that is being induced to the members. So the real moment that you will have to consider in the design would be H times L plus V times L times delta. And the N times delta is the additional moment coupled due to the axial force acting through the relative transverse displacement of member effects. So in that case, if you are using the red moment diagram to design the members, you are going to underestimate the bending demands of the members, and you're going to under-design the members. If you are using the blue curve here, this is the right thing to do, but the question is, how can you get this blue diagram so you can do this correctly? Or in other words, do you always have to consider the blue, or there could be ways where you could perhaps neglect the blue and stay with a simplified moment diagram, which is the red. So if we would like to assess the importance of P delta effects according to our design standards, this can be done by checking what we call the story stability coefficient for a frame. And in this case, theta, which is called the story stability coefficient, is being computed as the N total. This is the total gravity load above the story considered in the seismic design situation, times delta R, which is the design story drift, and this shall be carefully calculated for seismic effects, divided by V total, which is the total seismic story shear force based on elastic analysis, times your corresponding story height, which is commonly called interstory height. So this quantity here is normalized quantity, it doesn't have units. And as long as your stability coefficient is less than 0.1, then in that case, although the frame is deflecting, you can neglect the second order effects because they are not anticipated to be very large, and the effects on your frame are going to be very minimal. However, it's not always like this. You have to be a little careful with this aspect, simply because if the stability coefficient here is larger than 0.1, then there are a few other cases that you have to consider in your design evaluation. What are these cases? So if you compute the stability coefficient and it is between 0.1 and 0.2, then the second order effects may be approximately considered in your analysis by multiplying the relevant seismic action effects by a factor that is equal to 1 over 1 minus theta. So if we assume that by first order analysis, the moment is, say, 100 kilonewton meters, okay? Kilonewton meters. This is based on first order analysis, and your stability coefficient is, say, computed to be 0.15. Then, if you want to calculate the moment by considering the amplification of second order effects, this would be 1 over 1 minus 0.15, as I said, multiplied by m. And this moment is going to be the amplified moment that you can consider directly to design the member. Now, This approximation has been generated based on stability considerations of members. And it's simply a simplification to approximately consider, as we say here, peak delta effects in the member design without having to do what we call nonlinear analysis. However, you cannot approximate the member effects in all cases with this quantity here. So if the stability coefficient is between 0.2 to 0.3, then the second order effects should be considered by conducting nonlinear static analysis explicitly. In order to be able to do this, you will have to first come into the next semester and take the nonlinear analysis class, or you have to take a nonlinear analysis class, so that you could be able to do the nonlinear static analysis explicitly by writing the equations of equilibrium for the entire frame structure that you have under the formed configurations. And in that case, you will be able to measure explicitly the effect of peak delta on the member forces. Of course, there's the last case where your stability coefficient, when you calculate it, is very large, 0.3. In this case, by design, it is not permitted to design a structure like this because it is considered to be too flexible. So what you have to do is you have to go back to your original design. You have to modify the member sizes so that the theta becomes less than 0.3. If it's less than 0.2, you have the option to be with this case here, and you can amplify member forces accordingly. Now, in our seismic, in our design standards, in this case, SIA 263, but also in 262, the stability coefficient is there. So here's the quantity called theta. Be careful a little bit with the notation. So delta here corresponds to what I was writing before, delta R. H is the same. Sigma VED is basically what I called before N. So it's going to be the axial load that your frame carries above story I. And then H capital is basically the horizontal force that you anticipate to have on the system that is going to give you the first order shear. So again, if your stability coefficient is less than 0.1, then what we discussed before applies. Otherwise, you have to watch out if you are between 0.1 and 0.2. Now, the problem is that so far in what we discussed, we assume that the material or the members are going to remain elastic, and they are not going to anticipate, we're not going to anticipate any inelastic behavior. So basically what we assume is that members and the structure in general have been designed to satisfy the elastic strength demand F0. However, as we discussed previously, generally structures have a finite strength, but usually we know what it is. When we refer to the lateral strength, because we are dealing with seismic loading, this lateral strength, let's call it Fy. So what happens here is that once a structure becomes nonlinear, it will exhibit inelastic deformations here. And these inelastic deformations essentially will define what we call the maximum tolerable ductility demand that I can define as Greek letter mu. And this is equal to the ratio of delta max divided by delta y. So delta max is equal to the plastic deformation plus the elastic deformation that I have here. So mu here, or mi, is equal to 1 plus delta p over delta y. So the maximum tolerable ductility is a quantity that will always be larger than 1. And if I have no plastic deformation, so I have no plasticity in the structure, then the maximum tolerable ductility is going to be equal to 1. It doesn't go below than 1. Now, what I'm trying to say is that, in reality, if we design a structure to get into the inelastic range so that we can dissipate the energy because of the seismic event, we have to take into account the fact that we also have to carry the gravity load, because since I anticipate large deformations here, or I anticipate inelastic deformations, then the implication will be that P delta effects will also increase, and I'm going to have the problems that I discussed a bit earlier. I can demonstrate this through a simple experiment that we did some time ago here at EPFL. So here you have an electric sake table. Here's the MOLA kit that you are all familiar with from Professor Nussbaumer's steel class, or if you took structural dynamics in the last semester, you saw the demonstrations we did with the same kit. So what happens here is that I will demonstrate what is the implication of nonlinear response in addition to P delta. So the frame here is experiencing an earthquake, and because here the connection in fact breaks, essentially I have nonlinear behavior, and because of the nonlinearity, I have a complete different change in stiffness, and you see that my frame essentially collapses simply because the gravity has been offset by a very large displacement, and this second order shear essentially makes the total lateral resistance of the frame equal to 0. So if I go back here and I monitor carefully, you see that, the minute that, I have loss of strength here because I have detachment, I have a complete change in stiffness, and eventually the frame collapses because the gravity load that is sustained here from the plate essentially creates a second order shear and makes everything collapse. Now, if you think that this is fictitious, in fact, you can see here this frame. This is recorded during the Nepal earthquake, this video. And you see that once the earthquake occurs, the actual frame structure that was there essentially experienced the same type of collapse, exactly because of the same reason. So basically the connections experienced damage, then the frame displaced a lot, and what happened is that gravity induced high second order shear in the elements, and eventually the entire frame collapsed. And of course, if you are looking into buildings such as the one here, this is a 4-story building that was tested on a sake table several years ago, you see that because of the development of a first-story mechanism here, when I measure here the moments that I anticipate because of lateral load, these moments are essentially amplified, and eventually the frame loses stability because I have also the formation here of plastic hinging here in this position and this position, and I have the development of soft story mechanism here that essentially is not able to hold gravity because of large lateral deformations here. And obviously, wherever load comes from the top of the structure will amplify my shear bending forces in the columns. And here, because we are monitoring the first story drift angle or the first story drift ratio, you see that by the time that I'm reaching a certain deflection, see that this lateral deflection starts to become very large because I have instability in the structure. So I can describe the previous problems with a very trivial mathematical model. So here I have a frame that experiences lateral force H and vertical load N equal to N1 plus N2. And the corresponding linear system in this case essentially is subjected to V0, delta 0, if I neglect the effect of gravity and the possibility of having material nonlinearity in my system. Now, in the examples I showed you earlier, you saw that when I have lateral deformations because of the seismic loading, there could be a possibility of having damage in the ends of the member. And that would mean that once my frame reaches a critical displacement here, it will essentially enter into the nonlinear regime by hitting a strength equal to Vy. And that would result into a loss of stiffness that could potentially be zero if worse comes to worse. And this will be accompanied by a very large displacement that essentially will shift my gravity load, and it will create additional forces in the members because of the delta effects. So in reality, if I want to consider the influence of gravity here, this curve is going to look like the red one, where in terms of capacity, my system is not going to have Vy, but it will have a bit less than Vy. How much less? 1 minus theta. Theta is the stability coefficient. And if you are out here, the actual capacity of my frame is not going to be Vy, but it's going to be Vy minus n times delta divided by h. So the more deflection that I allow, so the more delta I allow, the more strength I'm actually losing. And of course, if I project this line and I go all the way to the point that it hits the zero axis, this would be the point that essentially will correspond to collapse. So this is an important consideration for seismic engineering because, as you can imagine, when you are designing a system and you are allowing it to deflect a lot, so you're not just looking at strength, but you're neglecting. You're just looking at strength, but you're neglecting deflections. The implication could be that you may have collapse because of the delta effects. So you can illustrate this aspect of having nonlinearity in the system and geometric nonlinearity also in the system by analyzing the response of different single degree of freedom systems and by changing the stability coefficient accordingly. So here I am analyzing a single degree of freedom oscillator with a 0.5 second period and 5% damping ratio. And I'm using the L-centro ground motion to illustrate the phenomena. And notice that I'm doing the analysis for 3 different stability coefficients ranging from 0, so basically I neglect gravity, 0.025 and 0.05. And each time I am dealing with different degrees of nonlinearity. So Q equals 1 here essentially means that if I go back to this figure, my V0 and Vy are basically equal to 1. So basically, I assume that I am not reducing at all the strength of my system in the seismic design condition. So essentially, I have an elastic structure. So you see that when I have an elastic structure, the stability coefficient when it ranges from 0 to 0.05 has practically no implication into the seismic response of this oscillator. Now, in the second case, I consider that my V0 divided by Vy is basically equal to 4. So what this means is that I am designing a system that I will allow it to be nonlinear, and the strength that I will have will be 4 times smaller than the corresponding design strength of the equivalent linear system. So in this case, the effect of gravity, you see that is important because the system that is essentially allowing for higher second-order effects to be induced in the system, in this case, will result to larger displacement demands relative to the case that I neglect gravity, and ultimately, I will have a larger residual deformation after the end of the earthquake. Now, in the event that I try to design a very tactile system, so basically I reduce my seismic force by 8 times relative to the strength of the equivalent linear elastic system. You see now that the implication is that here, when I have the system by neglecting the effects of gravity, it tells me that although the system becomes inelastic, it basically has some residual deformation, but it doesn't collapse. But when I explicitly consider the gravity in the analysis, you see that for the system where theta is equal to 0.05, because my oscillator enters into the nonlinear response very quickly, eventually what happens is that it reaches a displacement here that is actually very high, and that implies that essentially it collapsed. So if I go back one slide and I clean a little bit this slide here, essentially what I did in this case is that instead of allowing my oscillator to enter the nonlinear response here, because I have reduced considerably the strength and I have come to a point that is somewhere here. This essentially enables the nonlinearity to act very quickly. And you see now in this case, the effect of gravity is actually going to let the system collapse. Whereas in the case that, the strength was much higher, though the system was nonlinear, the implication of the effects was not as detrimental. This is why you have to be very careful and balance strength versus stability so that you can avoid problems like this one. Now, one thing that is very crucial in this discussion is how can I estimate the corresponding maximum displacement of my nonlinear system, since I anticipate in seismic engineering to design structures to enter the nonlinear regime. But at the same time, I would like to keep my analysis simple because I don't want to do explicit nonlinear analysis for every project that I'm supposed to design a structure. So the answer to this question can be given by this diagram. So people have analyzed what is the corresponding maximum displacement of the nonlinear system versus the displacement of the equivalent linear system. And they've seen that for very stiff structures, so basically that would be a period range that would be, let's say, in this region, the variation between UR and U0 would be quite significant, could go up to 10 times bigger depending on the level of strength that you have and you're designing your stiff structure. But once you exceed, interestingly, period of 0.5 seconds, what happens really is that the two displacements UR and U0 are going to be more or less the same, because you see here that on average, these two displacements are more or less the same. So that would mean that you can apply what we call the equal displacement rule, where if you have a static model and you analyze it based on elastic forces, this model is going to be able to give you U0. And then if you have a nonlinear model and you know that your period range is above 0.5, you can basically assume that these will actually go to more or less U0. So with your static analysis model that's going to be elastic, you're going to be able to compute easily what would be your U0. And then you can directly use that into with the equal displacement rule to essentially estimate what would be the corresponding displacement that your nonlinear system would have, assuming that you are reducing the strength you are designing for by a certain value, and instead of designing for F0, you design for something smaller.
Okay, so one question you may ask yourself is what could be ways to handle frame stability? So the simplest parameter to control the lateral stiffness of a building is the lateral drift. This is why, for instance, in if you're taking the stability class, I am putting a lot of emphasis into the computation of lateral deformations. Or if you've taken the structural dynamics class, again, we saw several cases why computing the lateral stiffness is basically very important. So design story drift ratios that have been used range from 0.1% to 0.5% of the story height, and that is used for serviceability purposes. Generally, lower values are used for hotels, apartment buildings to prevent noise and movement in case that you have an earthquake that is not very large, but it will create some disturbance. Moreover, if you are doing this for a hospital, again, because in hospital we have sensitive equipment, we would like to use lower values in terms of design limits of lateral deformations to ensure that we don't have any problem with the actual equipment of the hospital. Now, for collapse prevention, or when you are checking the ultimate limit state, design story drift ratios are usually much larger than those that are used for serviceability. So in that case, there could be a limit of 2 or 2.5% that you are supposed to respect if of concern is collapse prevention. Now, with those things in mind, I'm going to show you now in our standards what one can find for serviceability and what one can find for collapse prevention, and in particular for damage limitation during seismic action that relates to serviceability. If you look at the SIA standards, I'm listing 263, but technically I don't refer only to steel, I also refer to other structures. In fact, there's nothing. If you look at the current version of Eurocode 8 Part 1.1, you're going to have limits for serviceability under an earthquake that is not the largest one that you have to worry about collapse, but one that is modest. And we're supposed to design structures for 0.5% when buildings have non-structural elements of brittle materials that are attached to it. 0.75% for buildings having ductile non-structural elements, and 1% for buildings having non-structural elements fixed in a way so as not to interfere with structural deformations. Now, these limits are very crucial, and the reason is simple, that during an earthquake, you may notice that a building may not experience substantial structural damage, but instead there is substantial non-structural damage simply because some of these limits have been violated. And as an illustration, I'm gonna show you some photos from two events that have taken place, one in 2011 from the earthquake in New Zealand, where you see here a building that has experienced considerable damage in the facades, also some damage in infill walls, and these are not considered to be structural, at least the ones from the infill. The one in the column is considered to be structural, or the one in the facades here is not considered to be structural damage, and can be controlled if we have strict limits for serviceability. Of course, the second event here refers to the earthquake in Chile in 2010. Here, Professor Miranda of Stanford University, who is a lead expert in non-structural component damage, as well as ways to minimize damage in non-structural elements, had identified several cases where structural elements here would be perfectly fine, but you see here a partition wall that has been completely crashed. And of course, the problem here would be that this building cannot maintain its functionality, not because of the structural elements, but because of significant damage in the non-structural elements. Now, our seismic design standards, when we consider the ultimate limit state, there are no explicit drift requirements in the SIA norms. If you look at Eurocode 8 Part 1.1, the current code, there's nothing. But in the second generation of the Eurocode provisions, there will be explicit drift limits for collapse prevention that will be referred to the individual materials as well as lateral load resisting systems. If you look at other codes, they have developed quite a bit of information on this. So for instance, the American standard ASC 7, last version is 2022. You see that for structures other than masonry shear wall structures that are 4-story or less, with interior walls, partitions, ceilings, and exterior wall systems, depending on the risk category of the building, you see that the drift limits could vary to 0.025 of the corresponding story height. I'm sorry. Or if it's a risk category 4, that would probably be a hospital. You see that the drift limit is strict for collapse prevention, and it's 0.015 of the corresponding story height. If you're dealing with masonry structures or shear wall structures, you see that drift limits are much more strict in this case, simply because these elements or these systems cannot deflect a lot, and obviously we will have to limit deformation to something much smaller. And of course, if you have structures that fall into different categories, again, you have to kind of group them and decide what would be the drift limit to consider for seismic design with a specific story drift limits. The Canadian code follows more or less what we saw in the US, but it kind of puts all buildings into the same bracket, and it only distinguishes with respect to a risk category, where a normal building, that will be an office building, would be allowed to go to a larger drift limit, in this case 2.5% of the corresponding story height, whereas high importance buildings such as hospital, administrative buildings, would not allow to go more than 1% of the corresponding story height. Notice here that there is no distinction between frame structures, office buildings, wall structures, masonry structures, and this, obviously, this type of limits we see would be more reasonable for frame structures that essentially accommodate larger deformations than wall structures. Now, with that in mind, I have set up an example for you to, in fact, to understand what is the implication between respecting strength and respecting stability and drift limits, and what could be the implication, the associated implication in the design process. So for this, I'm going to illustrate these two concepts with a single story steel frame that you see here. I assume that this is a massless frame supporting a dead load of 5,000 kilonewton at the beam level as shown below. And essentially, this is a mass lamp system, a lamp mass system, where the entire mass basically is carried in the beam. The frame has a length of 8 meters and a height of 3 meters that are marked in the figure. Each column is pinned at the base, and it has an HEB 240 oriented, as I show here, with a strong axis in the primary direction of loading. Notice that I'm using S355 steel, so that means that I have a yield strength of 355 megapascals. The Young's modulus for my calculations is basically 200 gigapascal. Here, this is a typo, I'm sorry about this. So the Young's modulus of steel, in this case, is 200 gigapascal, and the damping ratio of the building I consider to be 5%. The building is to be designed for the design spectrum that is shown here in this figure, but notice that the peak ground accelerations of this point has to be scaled down to 0.08 g. So in my calculations, I will consider the acceleration of gravity to be 9.81 meters per second square. And the first question I'm supposed to answer is if the strength of the HEB 240 is sufficient for this lateral load. So this means that the question at this stage doesn't consider what we discussed so far in terms of stability and drift limitations. And essentially, the problem asks me to evaluate the adequacy of the design with HEB 240s for the anticipated seismic load that I'm going to derive from the spectrum that you see here on the right of your figure. So to answer this question, first we're going to have to estimate a few things, and in particular, because I need the seismic action, I will have to compute the corresponding period of the single degree of freedom oscillator here. And of course, to compute the period, I'm going to have to estimate the mass and the lateral stiffness of my oscillator. So in this case, the beam here is rigid relative to the columns, as the problem states. And here the column is pinned to the ground. So basically it will deflect like a cantilever, as we've seen in the class. And that means that the columns will be the only elements that will contribute to lateral stiffness. So the corresponding stiffness is going to be 2 times the flexural stiffness of my cantilever. So in this case, will be 2 times 3i column divided by h to the power of cube. And of course, all the quantities here are known because the Young's modulus is going to be the 200 gigapascal for structural steel. The moment of inertia here is the moment of inertia that I am getting for an HEB 240 by using the AZS C5 manual, or if you haven't done your undergraduate steel courses in at EPFL, if you take a table to read the properties of the HEB 240, you will notice that the corresponding moment of inertia is going to be 112.6 times 10 to the power of 6 millimeters to the power of 4. The height of my columns here is 3 meters. And because I'm using kilonewton millimeters in my substitution, when I do the stiffness calculation, that would be approximately 5 kilonewton per millimeter. So that allows me to compute the predominant period of the system simply by using the formula 2 pi square root of m over k. And as we discussed in the previous slide, the mass of my oscillator is 5,000 kilonewton divided by g. Whereas the stiffness here is basically the corresponding stiffness that I just calculated. So if I make a substitution here in the period formula, I will compute what is the actual period. And in this case, it comes out to be 2.01 seconds. So if I go back one slide, since the period that I calculated is 2.01 seconds, it means that my period is within this range here. Okay, so in fact, my period is roughly here. So I can compute the corresponding value of my peak pseudo acceleration by using this branch, but I have to consider scaling it down to 0.08 because we said that everything is scaled down by 0.08. So coming back to this, the design value of my sorry about this. This is a small typo. Sorry about this. So for T1 equals 2.01 seconds, the pseudo acceleration is going to be 1.8 divided by T1, which is 2.01 seconds, times 0.08 g, because I need to scale down the spectrum to a peak ground acceleration of 0.08 g. So that gives me a pseudo acceleration of 0.07 g, and that's the one I'm supposed to use to compute my design base here that this frame is supposed to carry. So my design base here is going to be equal to mass times the acceleration I just computed, and my mass is 5,000 kilonewton divided by g, whereas A, it's been calculated here and essentially yields to that quantity. So when I do the substitution and multiplication, that gives me a design base here of 359.1 kilonewton. So this is the total base here, it's called VD, that is being carried by my frame. So here I have a column that is has the same properties with the column on the right, and that means that my VD is spread to half in one column and half on the other. So here I will have VD divided by 2, and up here I'm going to have a moment that is going to be equal to VD divided by 2 times the height, so that I can compute the moment up there because I have a cantilever column. So with this in mind, Each column will take VD over 2. So for this case would be 179.5 kilonewton. And my MD is going to be VD over 2 times H. So if I do the substitution here, I'm going to get a moment that is equal to 538,606.2 kilonewton millimeters. So these are the demands because of my seismic action. So now I will have to see from regular steel design if the ATB 240 column is going to be able to satisfy the requirement for shear resistance and the requirement for flexural resistance. So the strength verification of the column for shear, if you recall, is going to be computed as phi times AW times T tau y, which is Fy divided by square root of 3. And the phi factor in this case is basically 0.75 AW times Fy divided by square root of 3. So the CR area here for an HB 240 again will be computed based on the EZS C5 design manual or any manual that you can find the cross-sectional properties. And if you make the substitution here by considering Fy to be 355 megapascal, as we have S355 still, that will give me a VRD, which is equal to 405.7 kilonewton. And in this case, you see that the strength requirement for shear is satisfied. Similarly, if I would like to consider the strength verification of the column for flexure, I will compute my MRD to be equal to W elastic Y times Fy divided by gamma M1. So in this case, I'm considering that the element is going to remain elastic. So this way I'm using the elastic yield moment. And again, for an HB 240, you can use the table to compute pretty much your W elastic Y. So if you make a substitution here, the MRD is simply equal to 652,523.8 kilonewton millimeters, which is larger than the corresponding MD that I computed based on the seismic action. So that tells me that the member verification in terms of strength is okay. And in principle, if I was worried only about strength, as we've done so far, the situation would have been okay. However, in the second part of the same exercise, and with the same exact problem that I showed, I am not going to worry only about strength, which I just did so far, and I'm not going to repeat. But I'm going to ask the question if we should worry about second-order effects in the estimated forces. That means that I need to compute the stability coefficient and see where I am in terms of 0.1, between 0.2 to 0.3, or above 0.3, that is not allowed. The story drift shall not exceed 1% of the story height. So this is an additional requirement now that essentially I'm going to have to compute the lateral displacement for the seismic action. And then I'm going to have to compare if for this lateral displacement, it's going to be less than the allowable one, which is 1% of the story height. And if some of these conditions are not satisfied, I'm going to have to redesign the members to satisfy the above design criteria. So to begin with, we said before that the predominant period of the system was calculated to be 2.01 seconds. And the pseudo acceleration had been computed to be equal to 0.07 g. So here by the way, sorry, here, there's a small typo. This one is supposed to be like this. So if I put it back, okay. With the corresponding pseudo acceleration, I will have to compute the anticipated lateral deflection UR due to the seismic action. And for this, we're going to use the formula that we saw in the lecture notes from yesterday, where UR is simply equal to a pseudo acceleration divided by omega-1 square, or if I replace omega-1 with 2 pi divided by T1, my UR is equal to A times T1 divided by 2 pi square. So if I make a substitution here, I can compute pretty much UR directly, and this would yield to 72 millimeters lateral displacement for the seismic design situation. So with this lateral deformation, and knowing that the system is going to remain elastic, I will need to check the stability coefficient and the corresponding drift limit that I was given. So for the stability verification, I'm going to use the stability coefficient, which is going to be equal to N times UR divided by VD times H. And if I do a substitution here, N is 5,000 kilonewton. UR, I just computed for the seismic action, is equal to 72 millimeters. VD is the total base shear for the seismic action, and I calculated from the part 1 problem that I showed you a bit earlier for the strength verification to be equal to 359.1 kilonewtons, and my story height here is 3 meters, and because I'm using units in millimeters, I am actually using 3,000 millimeters here. Now, surprisingly, when I compute the stability coefficient here, I get the stability coefficient for this frame to be equal to 0.33, which is quite high. It means that the frame is very flexible. And because it is larger than 0.3, the frame shall be redesigned so that the stability coefficient is below 0.3. Moreover, if I do the drift verification, simply by dividing UR with the story height, I have 72 divided by 3,000. This corresponds to 2.4%, which is larger than the 1% allowable drift limit that I was given in the problem. So we can easily understand that although the strength requirements are respected with the HEB 240, the stability requirements are actually quite substantial, and the drift verification substantial, and we have to redesign the frame to satisfy the drift requirements. So this can only be done by increasing the lateral stiffness of the system, or in other words, by increasing the moment of inertia till we satisfy the lateral drift demand of 1%, and then checking back the stability coefficient, but also the strength requirements, because something might have changed, particularly because we changed the stiffness and we anticipate a change in the period of our frame. So I will try to do this, and because I had made this example parametric, potential member that can work in this case is using an HEB 500 as a column. And if I use SZS C5, I can in fact derive the geometric properties of this one, which is going to be a moment of inertia of 1072 times 10 to the power of 6, CR area of 6,840 millimeters square. The elastic section modulus 4290 times 10 to the power of 3, and the plastic section modulus for reference 4820 times 10 to the power of 3 millimeter to the power of cube. So because I'm going to change the member, I will have to recalculate a few things. The first one is going to be the stiffness, and in particular, the stiffness computation here is going to have to use now the this moment of inertia. So my stiffness now with an HB by 500 is going to be 47.6 kilonewton per millimeter, which is clearly much stiffer than the 5 kilonewton per millimeter that I calculated for an HB 240. So that will have an impact on my period. And in particular, the period of my oscillator is going to be different now because the stiffness here is going to have to be that stiffness. And after the substitution, T1 is equal to 0.65 seconds. Now, you have to watch out because since we are at 0.65 seconds, if I go back to the spectrum that I showed earlier, so here, 0.65 seconds is within this range here. Okay, so that means that if I need to compute the pseudo acceleration, I'm going to have to use 2.71 g scaled down to 0.08 g peak ground acceleration. So going back to the problem, where I did my calculations here. This is why I'm computing the pseudo acceleration as 275 times 0.08 g. So essentially that would mean a new seismic action of 0.22 g. So this is the implication. So if you change something, you will have to go back, correct your seismic forces because your period is now different. So in other words, your pseudo acceleration is also going to be different. Now, with this pseudo acceleration, I'm going to compute what is the expected lateral deflection due to the seismic action. And my UR is again A over omega 1 square. Doing the substitution with a new pseudo acceleration is giving me an anticipated lateral deflection of 22.75 millimeters. Now, I'm going to do the drift verification with a new UR. UR over H is going to be 0.8%, which is smaller than 1%. So the limit in terms of drift is now respected. And if I compute the design base here for the new seismic action, VD is going to be again M times A. M is equal to weight divided by G. A was just calculated in the previous slide as 0.22 times G. So my VD in total is going to be 1084 kilonewtons. So I can proceed to the stability verification. So theta is equal to N times UR divided by VD times H. Be careful because UR now is going to be 22.75 that I just calculated here. Oh, sorry. And my VD is going to be 1084 that I just computed from the line above. So the new stability coefficient with this increase in stiffness I had was 0.03, so not even close to 0.3, that 0.33 I computed before. And I was able to successfully reduce it to below 0.1, so no need to consider P delta effect amplification because the stability coefficient, in fact, now is very small. Now, let us do again the strength verification so that we can see if anything changed. So each column is going to sustain VD over 2, so that's 542 kilonewton. Notice the increase in the corresponding CR demand. And MD is 1,626,000 kilonewton millimeters. Now let's see what happens with the actual strength verification. When I do the strength verification of the column in CR, I will of course have to consider updating my CR area here to that of the HEB 500. And my VRD, if I do the substitution, is going to be 1051.4 kilonewtons, which is safely larger than the corresponding demand that I have from the seismic action. Now let's see what happens with flexure. If I, in the strength verification of the column for flexure, I consider using the elastic limit, so that would be W elastic Y times Fy divided by gamma M1, which is 1.05. Our MRD here is going to be 1,450,428.6 kilonewton millimeters, which is smaller than the MD that I just computed here. So now the question is, if you want to redesign the system so that it will remain purely elastic, or if you could consider something that you've learned in structural steel design, where you've heard that we are allowed to do plastic design because this is a class 1 or class 2 members, and plastic design is allowed. So if we want to do an elastic design, the member does not satisfy the column flexure requirements. However, because we are allowed to do plastic design in this case, we can use W plastic instead of W elastic here, as the cross-section respects the cross-sectional classification limits for class 2 profiles. So that being said, our MRD is going to be W plastic times Fy divided by gamma M1. And that will yield into an MRD of 1,629,619 kilonewton millimeters. That is a bit larger than the corresponding moment that I have from my seismic action. So therefore, plastic design would allow us in this case to satisfy the design requirements in terms of strength, stability, and drift limits. However, some inelastic deformations shall be anticipated because the seismic action exceeds the elastic bending moment capacity, which is equal to W elastic Y times Fy divided by gamma M1. So you see what is the implication once you start having both drift and stability requirements, in addition to those of strength. A frame that would generally satisfy, or a member that would generally satisfy the corresponding strength requirements does not necessarily satisfy all the verifications related to lateral deflections and in particular stability. Now, finally, before I close this session, I would like to show you through some examples some additional implications in seismic design because of stability and drift considerations. I will do this by examining some designs we did a few years ago with one of my PhD students, where we designed different types of buildings with moment frames, according to the American code in this case. And the moment frames were essentially placed here in the perimeter of the plan view in the east-west loading direction. And we also did designs where we used 5-bay moment frames, again placed in the perimeter. And here you see a snapshot of the 4-bay. Here you see a snapshot of the 5-bay. Now, what we were interested here was to assess what is the implication of different design requirements into what we call the system overstrength. Okay, so in particular, steel moment resisting frames were redesigned to assess the impact of different design requirements. So we had a group A, where we were conducting member stability verifications, axial load bending direction, drift limits, as well as cross-section slenderness. Group B was only considering member stability, drift limits, cross-sectional slenderness. Group C was basically considering member stability, cross-section class, but no drift limit requirements. And Group D was only considering member stability, no drift limit, and no cross-sectional class requirements. To be able to assess the implication on what we call overstrength in frames, flexible frames, we conducted nonlinear analysis for these frames. And in the nonlinear analysis, essentially, we keep track of the normalized base shear versus what we call the roof drift of our building. And the nonlinear analysis shows us what would be the maximum anticipated resistance that our frames are going to exhibit. And we can compute this limit relative to what we anticipate to be the elastic limit of these designs. And for group A, which is what we do in the code, we show that in this case, these additional requirements essentially create a system overstrength that is actually equal to 3, which is quite detrimental, quite large, when it comes to a seismic design. Whereas group C, which is when we waived the drift limits, showed that when we satisfy only strength requirements, as well as section classification, the corresponding system overstrength is literally marginal. How much? 10% higher than the elastic limit that we designed the frame. So collectively, when I'm measuring overstrength for different designs here in Group A versus Group C, you see that most of the system overstrength comes from drift limits that we have to satisfy simply because I will have to impose a drift limit. So that means that I will need to increase the moment of inertia of my members. And because I'm already satisfying the strength requirements, the implication would be that I will have bigger members than what I need for strength. And that will create additional overstrength into the corresponding design. Now, as you will find out in the next coming weeks, this has several implications when I design structures. This is an example on steel structures, but the same applies to concrete structure as well. If I select the beam here to carry my dissipative zones where they will dissipate the inelastic behavior, they will exhibit inelastic behavior during an earthquake, I will have to consider this amount of overstrength that is being created to design the column. And then once I consider designing the column, I will also have to consider this amount of overstrength when I design the foundation. Otherwise, when the earthquake excitation comes in, if I don't consider this logic and I don't carry this system overstrength into my calculations, I may have a weak link that could be an element that I don't want to damage, and in this case could be a column or the actual foundation. So with that, I'd like to thank you very much for your kind attention, and I will see you in the next coming weeks in class.